In this lecture, we are going to cover the topic of control for discrete time systems in the Z domain. And later on, there will be another lecture of control in the state space. In this lecture, we are going to cover different methods for control. The first class of methods are the indirect methods. The idea behind the indirect method is to design your control system in continuous time and then to discretize this control system in the discrete time domain, trying to maintain the properties that we have achieved in continuous time. Then another type of approach are the direct methods. In the direct methods, we design the controller directly in discrete time. And we will see different techniques. We will see techniques in the frequency domain for discrete time systems, in the Z domain using the root locus design, and we will see also analytical methods. Finally, in addition to these indirect and direct methods, there is also obviously standard regulators, so the use of PID controllers. That's exactly the same as in control of continuous time systems. So we are not going to cover PID controllers because this is something that you should already know how to implement a PID controller. And actually we saw this briefly in the first lecture, the lecture about the motivation behind this course. I have shown you two implementations, a continuous time implementation and a discrete time implementation of a simple PID controller. So before starting to talk about control in the Z domain, I want to make a disclaimer. So in these slides, I'm going to recall a concept that you should already know, and it's the concept of illicit cancellations. So you have to remember that when you are designing a controller, there are some cancellations that you cannot do. Okay? In particular, you cannot cancel in the transfer function unstable poles with unstable zeros. Okay? So if we go at the board for a simple example, and this is true both in continuous time and in discrete time, so let's do it in continuous time. If I have P of S that is S plus 2, S minus 1, and then we have S plus 3, S minus 1, you may be tempted to cancel this pole with this pole, but that is something that you cannot do. It's an illicit cancellation. And now I'm going to explain, I'm going to recall, because this is something that you should already know, why you cannot cancel this. Mind you that if you have also something like this, okay, you can cancel this with this. You can make this simplification. The reason is that this is a stable pole, and it can be cancelled with a stable zero. But you cannot cancel an unstable pole with an unstable zero. And now I'm going to make an example to make you understand why this is not possible, even though this is something that you should already know, and is true both in continuous time and in discrete time systems. Okay? So the example is the following. I have a transfer function that is the following, and I write also the differential equation associated to this transfer function. And the differential equation, so computing the inverse Laplace transform, okay, is the following. So if we compute the Laplace transform of this differential equation, we will obtain a input-output transfer function that is the following. Let's analyze better this transfer function, and we see that this transfer function is actually equal, so h of s can be written as s minus 1, s plus 3, s minus 1. So we are tempted to cancel this and write that this is equal to 1 over s plus 3. Then, if I ask you, is this system asymptotically stable? Well, if you look at this transfer function, the answer is yes. This system is asymptotically stable because there is only one pole that is in the left-hand side part of the plane, okay? But is this differential equation, the state of the solution of this differential equation asymptotically stable? So this is the question now that we are going to analyze, okay? So to do so, let's compute the transfer function, so the Laplace transform of this, okay? I want to point out that here x double dot means a second order derivative of x. So let's compute the Laplace transform of this expression, okay? So if I compute the Laplace transform, I compute the transform of this. So this is the transform, I'm missing a term. So this is the transform of the second derivative, okay? So the transform of the second derivative is this polynomial here, where this is the the S transform, the Laplace transform of x of t, and this is the initial condition of x of t, and the initial condition of the derivative of x of t. Okay, so we have the term, then we have plus 2s Laplace transform of x minus 2x0 minus 3x of s, the Laplace transform of this term, equal to s u of s minus u of 0 minus u of s. This is the Laplace transform of this, and this is the Laplace transform of this term. Okay? Now, if I solve this expression with respect to the Laplace transform x of s, what we obtain is the following three terms. Is s minus 1 s squared plus 2s minus 3 u of s plus s plus 2, and then the same denominator. And then this expression. So here we have that x of s is given by this expression. Now, at this point, you have to recall that when we work in the Laplace domain, when we work with the transfer function, we are always usually working with the transfer function between the input and the output. Okay, so in this case, x is the output. Okay, so this transfer function is this transfer function. However, x of s, okay, is actually may depends also on other quantities, okay? It may depends, for instance, on the initial condition and on the initial condition of the derivative, like in this case, okay? So to make things a bit more simple, okay? Oh, actually, I forgot another term, sorry. So there is also minus 1 over s squared plus 2s minus 3 u of 0, okay? So sorry, I forgot this term. So we have these four terms, okay? Now, to make things a bit simpler, let's assume that dot x is equal to 0. So the initial condition of the derivative is 0. And let's assume that u0, so the first input, okay, the input at 0, is equal to 0. If that's the case, then we can forget this term and this term, and let's work only with the remaining terms, okay? So let's cancel the board. So we are left with these two terms, okay? And let's focus in particular on this term here, okay? In the end, this is a linear system, linearity holds, so we can study the effect of these two terms in two different moments and then add them together. So let's study in particular this term. So the term s plus 2 divided s squared plus 2s minus 3 x of 0, okay? So I want to compute the inverse Laplace transform of this term over here. So first of all, I compute the partial fraction expansion, and what I get is the following. Okay, so this is the partial fraction expansion of this term. And now I compute the inverse Laplace transform of this term over here. And what we have is x of 0 divided 4 e power minus 3t plus 3 e power t. Okay, so we obtain this expression over here. And so the actual expression here, x of t, will be equal to something, okay, that depends on the input, okay, so it goes over here, plus that term over there. So now, if here we make the cancellation, if we're studying only this term, because for some reason we are not considering the others, we will have the conclusion that this system is asymptotically stable if we make this cancellation, okay, and we are left only with a stable pole. However, we have to remember that the transfer function that we are studying is only one of many transfer functions that actually appear in our system. This means that even if here the unstable pole disappears because we make an illicit cancellation, that pole will still be there for the other transfer functions. For instance, in this case, for the transfer function between the state and the initial condition. And what happens is that if the initial condition is different from 0, you see that we have an exponential that is diverging. So this system is actually unstable, okay, because for every initial condition that is different from 0, because we have this term here. And if we don't cancel the unstable pole here, we know that this is an unstable system. But if we do it, if we cancel that pole there, then we will miss this relation, we will miss this information, and we will think that the system is asymptotically stable, but that's not the case, because you have to remember in your block diagram there are multiple transfer functions, okay? And we're studying this because this is the most important, but it's not the only one, so you cannot do that type of cancellation. So this is important in particular when you are designing your controller, because you cannot design a controller that cancels an unstable pole, okay? That's the point, okay? And this is true both for continuous time and discrete time. So this is something that you cannot do, okay? Another disclaimer that I want to make is about approximate cancellations, and this is something that is true only for discrete time systems. And this is not something that, it's not a rule, but it's just an advice and something that you should keep in mind when you are working with discrete time systems. So if you look at the board, the problem is the following. Let's say that you have one pole over here. So this is the root locus of your system, and you have one pole close to the circle. One thing that you may want to do is to cancel this pole. Okay, so you put over here a 0 from the controller, so that the pole and the 0 cancel out, and then you have to, what you want to do is to move basically this pole closer, so you put it here. If you put it closer to 0, then the response of the system will be faster. So now what you are doing is designing a controller that cancels this pole, and it will move it closer to 0. This is possible, you can do it, because this is a stable pole, so the cancellation of this pole is allowed. However, in discrete time, you have to keep in mind that everything is an approximation. This pole that you see here is there because of approximation that you have made, okay? For instance, you are using a zero order hold, and you get this pole over here in your interconnection between the zero order hold and your system. However, the zero order hold is an approximation that is over there, okay? And, or at least how you are studying it, and we will see this in a little bit. And you have to keep in mind that this may not be exactly there, but it may be, for instance, a bit closer here, or a bit closer here, may also be on the unstable part, okay? The point is that the cancellation is not going to be an exact cancellation, and so some mess will going to happen around there. So this is just a warning, okay, that in practice you have to be careful when you make cancellations in discrete time, because the cancellation is not an exact cancellation. So after this disclaimer on cancellations, and I repeat that what I said is that illicit cancellation are cancellation of unstable poles with unstable zeros, but you can cancel stable poles with stable zero. In discrete time, just be a bit careful about this. This is in practice, okay? In practice, you have to be careful about cancellations in discrete time. In the exam, this obviously doesn't really matter because everything is given and everything is exact, okay? Okay, so the situation for indirect methods is the following. In the indirect method, we have our plant in continuous time, and we design the controller in continuous time, okay? So we design this controller to achieve some stability performance, or other type of performances like steady state accuracy, okay? So we design our controller in continuous time using the techniques that you have learned in previous courses. And now what you want to do is to discretize this controller, okay? So now you want to obtain a digital controller, okay, that is interfaced with a continuous time plant using a digital to analog converter, so a sampler and a hold device, okay? And you want to preserve the properties that you have designed in continuous time. So if you have your continuous time controller, and your continuous time controller makes the closed loop system asymptotically stable, you want that when you discretize this controller and you connect it with a hold, the interconnection of this plant and this controller is still asymptotically stable, okay? So we have to consider obviously the fact that doing a discretization, there will be approximations, and in general these properties are not preserved, okay? So we have to study basically different type of discretization algorithms, because depending on the discretization algorithm, some of these properties may be preserved and some no. Some discretization algorithms are better than the others because they preserve more properties than the other. Some algorithms do not even preserve stability, and obviously you don't want in general to use that type of discretization algorithm, okay? So what is the general procedure here? So before looking at this discretization algorithm, the idea is the following. Let's start with the assumption that we have designed a continuous time controller, okay? So we have the continuous time plant, and we have designed the controller in continuous time, okay? Now we want to discretize this controller. How do we do this? First of all, we have to select the sampling time, okay? So we have to select the sampling time of our controller or our discretized controller. And we want to have a study of the preliminary effects of the discretization, okay? And in case this preliminary study says, look, your controller cannot work, then we have to redesign the controller. So what is the preliminary study? Well, we know that if we are going to use a digital controller, we have to use also a zero hold or a hold device in general, okay? So for simplicity, we assume that the hold device that we use is a zero order hold, and we want to study the effect of the zero order hold. The point is simple. If we go back to our scheme over here, at first we have designed the controller for the plant. However, we know that between the controller and the plant there will be a hold device. So instead of designing the controller for just the plant, we have to design the controller for the interconnection of the zero order hold with the plant, okay? Because that zero order hold will be in the interconnection, so it's better if we keep it in mind immediately, okay? So we have to study the effect of the zero order hold. And the problem is the following, that the zero order hold has an exponential, okay, e power st, and this is not so easy to deal with classical techniques of control that you have seen in previous courses, because usually you always have a fraction of polynomials, okay? So instead of studying the zero order hold, the full description of the zero order hold, we study an approximation of the zero order hold to make things a bit simpler. And we see two different approximations. One approximation is the Padé approximation, and the other one is this type of approximation. So this approximation here on the right is something that we already seen, and we saw this while we were studying the effect of the zero order hold and the first order hold, and so during the lecture about sampling and reconstruction. And we saw that the zero order hold can be approximated basically with a delay term. Okay, so this is an approximation of the zero order hold. It's simpler with respect to the full description of the zero order hold. However, it's still not simple enough for us because in your courses of control, you didn't study delays and you don't know how to control a system that has delays. Okay? So for this reason, instead of studying, of using this approximation, we look for a different type of approximation, and we end up using the Padé approximation. Okay, so this is the Padé approximation of the zero order hold. How do we obtain this approximation? So the Padé approximation is in philosophy similar to the Taylor expansion of a function. However, the Padé approximation works better than the Taylor expansion when the function that we have that we want to expand has poles. So it's a fraction basically. When your function is a fraction, the Padé approximation is usually better than the Taylor expansion. How do we obtain that Padé approximation? So it's obtained in the following way. So we have our zero order hold that is described by this transfer function over here. So the first step is to factorize e power minus st divided by 2, and here we are left with this. And you see that if you multiply this by these two terms, you get back the same expression as before. And now at the denominator, we have s e power s t over 2. And at the numerator, we have what is left. Okay? Now we compute the Taylor expansion both at the numerator and at the denominator, and we have the following expression. So this is the Taylor expansion of the first term, the Taylor expansion of the second term, and then all the terms of order s square or over that power. Okay, we do the same expansion at the denominator. We simplify this term with this term, and then you see that at the numerator we get a term in s. So this s can be simplified with this s over here, and so what we obtain is t divided by 2 plus t divided by 2, so it's t divided. So we ignore the higher order terms, so the terms of power 2, 3, and so on, and we are left with this term over here, and this is exactly the term that we have on the slide. Okay, so this is the Padé approximation of your system. So the idea is basically instead of designing the controller for P of S, okay, you want to design the controller for this function over here. So you design the controller in continuous time for this function that we usually call HP of S, okay? So this function has an approximation of the zero order hold in itself. And so in this way, if we control this plant, this HPS, instead of this, we will be more lucky, we will have a higher chance that our controller will work also in discrete time. I want to point out finally that even though this approximation have the factor capital T, when you study the interconnection of the zero order hold with a plant, you have to remove the capital T. The reason is that when you implement, when you go from continuous time to discrete time, you will also have a sampler, And we saw that the effect of the sampler is to multiply by 1 over t, okay, so to have this gain, that will cancel out with this term over here. So we discussed this several times during the lecture on sampling and reconstruction. So this means that actually the approximation that we have to use in our analysis is the following. So going back to this, what you actually are want to study is this interconnection here. So HP of S is this function over here. Now that we have studied the effect of the zero over the old, and we are happy with our controller in continuous time, we discretize the controller to discrete time, okay? And after that, we have to analyze the properties of the closed loop system in discrete time. Because again, we don't have the guarantee that some properties that we have achieved in continuous time are preserved in discrete time in general, okay? So you have to do an analysis a posteriori, so after that you implement the controller to see what is the behavior of the discrete time system. Let's now focus on two steps, and the two steps are the selection of the sampling time and then the discretization of C of S. So for the selection of the sampling time, there are some rule of thumb basically. So these rules are there because they work, okay? In general, you can select the sampling time using these rules. There is not a real theoretical reason why these selections, these rules work, okay? But in general, if you follow them, you will get a discrete time system that actually behaves as you expected, okay? So there are different rules that you can apply in different situations, okay? So in the first case, if you have your C of S, the frequency response of your controller in continuous time is of low pass type, then omega S should be larger, much larger than the cutoff frequency, okay? So what does it mean? What is the cutoff frequency? Well, the idea is the following. So you basically have, if we represent the frequency response, so here we have omega on this axis, if your response is of this type, okay, so here we have the cutoff frequency, okay? So this is a low pass, the controller is of low pass type because, as you see, it's preserving the low frequencies while is attenuating the higher frequencies. Then we want to choose omega S much larger than this frequency here, okay? So this omega S has to be far away. And the reason is that the omega S is linked with the sampling time. So if you select an omega S that is much larger than the cutoff frequency, you are actually selecting your sampling time, okay? Other rules that you can follow are the following. So the sampling time should be consistent with the dynamic properties of the continuous time closed loop system. So if your closed loop system is a chemical plant in which the reaction happens in hours, then there is no point in selecting a sampling time that is a millisecond because everything is extremely slow, okay? However, if instead your plant is actually an electric circuit in which the dynamic is extremely fast, then you have to select the sampling time very small, okay? So you have to select the sampling time depending on the dynamic properties of the continuous time closed loop system. And here there are some rules to assess these dynamic properties, okay? One property that you may want to satisfy is to select a certain settling time, okay? So you want that the continuous time closed loop system has a certain settling time. So if you have a certain settling time Ts, then you select the sampling time with this rule over here. So the sampling time has to be between Ts over 10 and Ts over 4, and you can select it as you wish, okay? In general, this is a good selection. It means that in practice, this works and it will allow you to reach, if everything else is selected correctly, the settling time that you want to achieve, okay? Again, there is not a theoretical reason why this is working. This works in practice, okay? Then another rule is to select the sampling time in this range, okay, where this range depends on the frequency, on the natural frequency of the dominant poles, okay? So here I want to point out what are the dominant poles and what is the natural frequency. So if you are in continuous time, okay, and this is the root locus, then you may have a situation like this, okay? So these are the poles of your system. The dominant poles are these poles over here, okay? So are the slowest poles, okay? The closer you are to the imaginary axis in continuous time, the slower is the response due to that pole, okay? And so it means that these are the slowest, and those are the dominant poles. The reason why are the dominant is because the steady state will not be reached because of these poles, because they are the slowest. Okay, so they are the dominant poles. The effect of these other poles is going to disappear much faster than the effect of this pole. Okay, so we have those two poles. So it means that in your transfer function, you will have a polynomial of second degree in the denominator. Okay, so this is one of the polynomials. You may have other factors there and other factors here. But now we are focusing on this factor over here that is associated to these two poles here. So this is a second degree polynomial. And for instance, let's make the example s squared minus s plus 1. Okay, so we have this polynomial over here. What is the value of zeta and what is the value of omega n for this polynomial over here? Well, we have that 2 zeta omega n is equal to minus 1, and then we have that omega n squared is equal to 1, okay? So this basically means that omega n is equal to plus minus 1, okay? However, this is a frequency, so it has to be positive, so we select only the positive solution. Omega n is equal to plus 1, and then here we can compute zeta, and so zeta is equal to minus 1 over 2, okay? So we have omega n and we have zeta, and this can be done for every type of this polynomial. And these are polynomials with that have complex solutions, okay? So it means that it corresponds to two pair of conjugate points in the complex plane, okay? So we said, if you look at the slide, that you want to select t between these two ranges where omega n is the natural frequency. If we look back at the slide, this is the natural frequency. What is the natural frequency? Well, here, since you have complex poles, you will have some oscillations. You will have a sinusoid. And since you are in the left-hand side of the plane, this oscillation will decay to 0, okay? So these two effects are explained by these two values, okay? So this is basically the frequency. The natural frequency is the frequency of the sinusoid associated to this pole when the damping is equal to 0, okay? So we have discussed how to select the sampling time. Now we want to discuss a different type of discretization algorithm. So we have a selection of discretization algorithm, and now we are going to see how to derive, how we have found these discretization algorithms. To explain the discretization algorithm, we look at the board, okay? And we start with a simple example. So we want to discretize this transfer function here, okay? So we want to find a rule to discretize this transfer function in which there is just one pole, basically, okay? So to do so, we apply the following strategy. We first of all compute the differential equation associated to this transfer function. So we compute the inverse Laplace transform, and we obtain this differential equation associated to this transfer function. So if you compute the Laplace transform of this, the input-output transfer function is given by this expression over here. So we have this transfer function, and so we have this differential equation, and we want to compute now x of t, okay? So to do so, we bring this on the other side, and we compute the integral. So we have that x of t is equal to the integral between 0 and t of everything that is on the right-hand side, okay? Now, we want to discretize this integral. So to compute x at the time kt, this is equal to the value of x at the time kt minus capital T, okay, so at the previous sampling time, plus the integral between the previous sampling time and the current sampling time of this function here, okay? So from this point to this point, this relation is exact, okay? So at this sampling time, this is equal to the value of the previous sampling time plus this integral. When we go to discrete time, we have to approximate this integral over here, okay? So the approximation arrives at this point when we are discretizing this integral. How do we discretize this integral? So to do so, to explain different ways to do this discretization, we represent this function here, okay? So this function under the integral is represented over there. And now we put ourselves here in kt minus t and in kt. And I want to basically approximate the integral between these two terms. So basically I want to approximate this area here, the area under this curve, okay? So there are different ways to approximate this area. And the first way is to approximate it with a forward rule. So basically what we do is that we put ourselves here and we approximate the integral keeping the value constant, okay? And we compute this integral in this way, okay? So the approximation of of the area below this curve is approximated with this rectangle over there, okay? So if we do so, we have that xkt is equal to xkt minus t, and then we are approximated this integral basically in this way. So the base of this rectangle is capital T, and then the height, okay, is just the value of the function at this point over there. So we have times minus a x of kt minus t plus a u of kt minus t. Okay, so we have integrated this. We have approximated this integral with this expression over there. Now what we do is that we compute the z transform of this expression, because now we are in discrete time, and we then find the transfer function between x of z and u of z. You can do the computation by yourself as an exercise, and what you should obtain is the following. So you should obtain this transfer function, okay, and so this is h of z approximated using this forward rule, okay? So you put ourselves here and you look forward, okay? So we can call this hf of z. So if now we compare h of s with with hfz, okay, we see that s has been replaced by z minus 1 divided t. Okay? We can also divide and multiply by z if we wish, and we get 1 minus z power minus 1 divided z power minus 1 times t. Okay? So this is basically the first rule that we obtain. Okay? So if we approximate this integral with the forward rule, then the mapping between s and z is given by this rule. So if you look back at the slide, we have obtained the forward difference rule over here. So s is equal to z minus 1 divided capital T. Now let's try to approximate this integral, okay, using another rule. And another way is that we put ourselves over here and then we look back, okay? So this is the backward rule when we approximate that integral with this rectangle over here. Okay? So I write in blue, just to show that now I'm referring to that particular approximation. So x of kt is equal to x of k t minus t plus the base is the same, so is capital T. And then the height of that rectangle now is minus ax of kt plus au of kt. Okay? So at this point we compute the z transform and we write the transfer function x of z divided u of z, and this will in this case be equal to a divided z minus 1 tz plus a. Again, you can do this as an exercise. You can write this and you obtain that, and this we define this as hb of z, and we compare the two transfer functions and we see that the rule this time is that s is equal to z minus 1 divided tz, or if we write this as a function of z power minus 1, is 1 minus z power minus 1 divided t. Okay? If we look back, we have found the backward difference rule. Okay? Let's do a last one, and the last one is to use the trapezoidal rule, so to we approximate this area using the area of this trapezoid. Okay, so to do so, we write here the computation. So we have x of kt is equal to x of kt minus capital T plus. Now we want to compute the area under that trapezoid, so that the area of that trapezoid, so it's t over 2, and then we have minus ax of kt, minus t, minus ax of kt, and then we have plus au of kt minus t plus au of kt. Okay? So we obtain this expression. Again, we compute the z transform, and then we compute the transfer function between xz and uz. And what we obtain is the following. Okay? And we call this hz with a little t over there. So the reason is that why we call this ht of z is because if you want, we are using the trapezoid rule, or this is also called the Tasting rule, or is also called the bilinear rule. So it has different names. Okay. And if we look at the mapping between s and z, we have that s is equal to 2 over t, z minus 1, z plus 1, or if we want to write it with powers of z minus 1, then we have 1 minus z minus 1, 1 plus z minus 1. Okay? So why is called bilinear transformation? Well, you should know at this point because the mapping between s and z has this expression here, and you know that if you multiply the numerator and denominator for this value, sorry, if you multiply left and hand side for the denominator, you get an expression that is bilinear in s and z. Okay, so this is the same, very similar to the expression that we saw for the analysis of the stability. So the expression that we have used to use the route criterion in the w with the w variable. Okay. So if we look at the slides, we have obtained these three rules: the backward difference, the forward difference, and then the bilinear or Tasting transformation. Now what we want to study is if these transformations preserve or not stability. So to study if stability is preserved or not by these discretization algorithms, we have to see how the left-hand side plane, complex plane, is mapped in the discrete domain. Okay? So let's start with the first rule. So the first rule is the forward difference in this case. Okay, yeah, I start with the forward difference. And let's invert that. So we have that z minus 1 is equal to st. So z is equal to st plus 1. Okay? So what does it mean, this? It means that if this is the complex plane, okay, and we want to map this in the z domain, and I sketch here the circle, okay, we see that what's happening is that this half plane, so if we replace this half plane in this equation, what happens is that this half plane is multiplied by t, so by a scaling factor, doesn't change much, and then is shifted plus 1. So it means that when this is 0, we are in plus 1. So it means that that semi-plane is basically mapped over here. So you see that this discretization algorithm does not preserve stability, because if we select a point that is over here, this will be mapped somewhere over here, and we don't have a guarantee that it will be inside the unit circle. So this method, the forward difference, does not preserve stability. Let's now analyze the second method, the backward difference, and to do so we first have to invert that expression. So we have tzs equal to z minus 1, okay? We bring this on the other side and we factorize z. So we have z that multiplies ts minus 1 equal to minus 1, and so we have that z is equal to 1 over 1 minus ts. Okay, so we have this expression, and now we want to understand what this expression represents. Okay, so we saw that the previous expression was easy and it meant just a shift of the plane. What this means? So to do so, we have to do some operation. First of all, we subtract 1 over half from both sides. So we have z minus 1 over half equal to 1 over 1 minus ts minus 1 over half. Okay. Now we do this operation. So we have 2 minus 1 plus ts divided 2 times 1 minus ts. This simplifies, and then what? Okay, let's write it over here. So then we have z minus 1 over 2 on the left hand side, and on the right hand side we obtain 1 plus ts divided 1 minus ts times 1 over 2. Okay? Now we compute the absolute value of this and the absolute value of this, and what we are interested is where the imaginary axis is mapped. So s will be equal to j omega. So this means that if s is equal to j omega, this absolute value is actually equal to 1 over 2, okay? Because this will actually, the absolute value of this will be 1, okay? So we have this equation over here, that z minus 1 half in absolute value is equal to 1 half. And this is the geometric, so the geometric interpretation of this is basically a circle of center in 1 half and radius equal to 1 half. Okay? So it means that the complex plane, the left-hand side of the complex plane, is mapped in here, okay? So where this is 1 over 2. So it's a little circle of radius 1 over 2 and is centered in 1 over 2, okay? And the left-hand side plane is mapped there. Also, this transformation does not preserve stability. The reason is that what happens is that the points that are not in the stable part of the plane may be mapped, for instance, in this point here, and so they may look stable even though they are not. Okay? So this transformation does not preserve stability. Let's now look at the last transformation. So the last transformation is the Tustin transformation. That is actually a bilinear transformation. So we already know that actually preserves stability, and we already proved it in the lecture about stability. We can also prove it again in this case in a different way, okay? And so we first invert this expression, and we know that the inverse of that expression is going to be this one because we saw it already in the previous, in one of the previous lectures. Now we want to compute the absolute value, and we want to map the imaginary axis, so S is equal to j omega. So the absolute value of this, once we replace j omega, is actually 1. So you see that this is a circle centered in 0 with radius 1. So it means that we are mapping the left-hand side complex plane inside this circle. So this transformation preserves stability. So we have seen that the first two transformations, backward difference and forward difference, do not preserve stability, while the Tustin transformation preserves stability. However, we may want to try to find a different transformation that preserves stability, that have better properties with respect to other characteristics, okay? So the next transformation is basically a modification of the Tustin transformation in such a way to preserve some additional properties. So the Tustin transformation, we saw that introduced some distortion. We discussed this in the lecture about stability, and the reason is that the real mapping between the S domain and the Z domain is the one with the exponential, okay? So this means that this is an approximation, there will be some distortion. Can we make some of this distortion less severe? So this is at the base of the transformation with pre-warping. So this is an obvious modification of the Tustin transformation, in which basically we have replaced 2 over t with this factor over here. Okay, so what does it mean this and what this represents? So to do so, we go and we look at the board. And what we compute now is, given our h of s, so we have h of s is equal to a over s plus a, we want to compute the power of h of s. To compute the power, we have to compute the frequency response, then the absolute value, and compute the square of this value. And this is equal to a squared divided omega squared plus a squared. And this is equal to 1 over omega squared divided a squared plus 1. So you see that when omega is equal to a, we have that h j omega in absolute value square is equal to 1 over 2. Okay? So this gives us an interpretation of the pole of a transfer function. So a pole is the half power point. So is the point in frequency for which the power is equal to 1/2, okay? So now we want to preserve this property in discrete time. We want that in discrete time the half power point is a, okay? Let's see, first of all, what happened to the half power point when we use the Tustin transformation. So if we use the Tustin transformation, we have ht of z. And the first thing is we have to compute the frequency response of this. To do so, we have to replace z with e power j omega capital T, okay? Because we saw that in the z domain, the frequency response is not found replacing just j omega, but actually we have to replace e power j omega t. So this is equal to a divided 2 over t e power j omega t minus 1 e power j omega t plus 1 plus a, okay? And now we can use the Euler rule here to write, so we factorize the exponential, we write this as the fraction of a sinusoid and a cosinusoid, and so we obtain actually a tangent. And so after some computation, we obtain basically 2 over t j tangent of omega capital T divided 2 plus a, okay? Now, if we compute the half power point, okay, so for this you want then to compute the absolute value, okay? So we compute the absolute value, and you want to compute the square, okay? You see that the half power point is achieved when 2t tangent of omega t over 2 is equal to a, okay? So you see that now it's not true anymore that the half power point is omega equal to a, but omega has to satisfy this quite complicated expression, okay? So how can we modify the Tustin transformation in such a way that the half power point is preserved, okay? To do so, well, the idea is quite simple, okay? So the original Tustin transformation is basically htz is equal to 1 over 2 over t z minus 1, z plus 1 plus a, okay? So this is the original transformed transfer function with Tustin, okay? So let's now put here alpha. If I put here alpha, and I repeat this analysis, I will get alpha over here, okay? Now, if I select, and let's write it here, okay? So I select alpha equal to omega 1 over 2 capital T tangent of omega 1 t divided by 2, what happens is that if I replace alpha over here, the 2 over t simplifies, and here the j, when omega is equal to omega 1, will simplify, and what we will obtain will be basically the expression of absolute value of a divided j omega 1 plus a in absolute value, and then we have to compute the square, okay? If omega 1 is equal to a, then we obtain that the half power point is actually equal to a, okay? So basically, using this pre-warping expression, so this deformation of the Tustin transformation, what we obtain is that when omega is equal to omega 1 and omega 1 is equal to a, we obtain that the half power point is actually obtained in the original half power point. Now let's go on other discretization algorithms. These are basically simpler than the ones that we saw up to this point. So one simple algorithm is the impulse response invariance. So the idea is simple. We have the continuous time Laplace transform, and then we, in the controller, and then we compute the inverse Laplace transform, and this way we compute the impulse response of the controller, and then we compute the Z transform of the impulse response, and we obtain the discretized controller, okay? So this is obviously a quite straightforward method. We just compute the inverse Laplace transform of a Laplace quantity, and then we compute the Z transform of a time domain quantity, and it's a possibility. This obviously preserves stability, and in addition preserves also the impulse response. The reason is that if we go from, if we compute the inverse Laplace transform of C of S, we are computing the impulse response of C of S. And then the Z transform of the impulse response will give us C of Z. It means that the discrete time version of the controller and the continuous time version of the controller have the same impulse response, because we have used the impulse response to go from one domain to the other, okay? The next discretization algorithm is the step response invariance. The idea here is that instead of preserving the impulse response, we want to preserve the step response properties. We know that the step response properties from the lecture on performance depends on the number of zeros in 1 for discrete time, and similarly for continuous time it depends on the number of zeros in 0, okay? So we know that the 0 in 0 actually in continuous time actually correspond to the 0 in 1 in discrete time. So the idea is the following. We want that the discrete time has a 0 in 1. So to do so, we first have to remove basically a a 0 from C of S. So C of we take C of S, we divide it by S, we take the inverse Laplace transform, then we take the Z transform, and we multiply for 1 minus Z power minus 1. The reasoning here, the logic behind this is that C of S will have a 0 in 0, okay? So we want to preserve this, and we want to map this 0 in 0 in a 0 in 1 in the Z domain. So we first remove that 0, we invert the expression, we go to the Z domain, and then we map, we add the zeros that we have removed in the right position. Okay, so this is the logic. Finally, the last algorithm of discretization is the pole zero correspondence, and this is one of the nicest algorithm that you can use, and is one of my favorite actually. And the idea is simple. Basically what you want to do is to map exactly the location of a pole or of a zero from continuous time to discrete time. Okay, so you know that a pole is in continuous time is mapped in discrete time in the following way. Because we have seen that if we compute, if this is a pole and we compute the inverse Laplace transform of this pole, this corresponds to an exponential, okay? And that exponential, so an exponential of time, if we compute the Z transform of that exponential of time, we'll obtain a fraction 1 over this polynomial over here, where we have e power minus at, okay? So this is, we have seen this basically when we were talking about the Z transform. So we know that if we go from a function that has a pole in S plus A, this will become, using the impulse response invariance, pole in this point over here, okay? The problem of this method is that this pole is actually an easy pole to map, but there are other poles and zeros, another characteristic of our controller that we have to map, okay? And these are not so straightforward. So one thing that we have to map is the zeros at s equal to infinity. What is a zero at s equal to infinity? So what is the zero of our transfer function? So if we look at the board, so if we have h of s and we have a certain denominator, at the numerator we may have something like s minus a times something else. So a zeros is a value of s for which this transfer function is equal to 0. So s equal to a is a 0 because for that value of s the transfer function is equal to 0. However, let's now consider a transfer function that has a relative degree, okay, different from 0. So you know that the relative degree is the difference between the degree of the denominator and the degree of the numerator, okay? Now let's call the relative degree r, and let's say that r is greater than 0, okay? What does it mean? It means that the degree of the denominator here is greater than the degree of the numerator. Now, if we compute the limit with s that goes to infinity of h of s, when the relative degree is, for instance, equal to 1, okay, s is going to infinity, so this means that the fraction will actually behaves like 1 over s, and as s goes to infinity, this goes to 0, okay? So this means that the point s equal to infinity is actually a 0 of our system, okay? And in particular, if we have a certain relative degree equal to r, then it means that our transfer function has r zeros at infinity. And now we want to map the 0 at infinity. How do we map the 0 at infinity? What does it mean at 0 at infinity? Well, it really depends how we want to interpret this. And one way to interpret this is the following. Let's say that we are going to infinity, so s is going to infinity, but you can go to infinity in various ways in the complex plane, and we select as a way the moving on the imaginary axis. So we are basically going to infinity, going towards, staying on the imaginary axis and going up. So this means that when s goes to infinity, j omega is going to infinity. And obviously this means basically that it's omega that is going to infinity. So omega represents the frequency, and we are saying that the 0 at infinity is basically the 0 at the maximum possible frequency, okay, when the frequency goes to infinity. But what is the maximum frequency in discrete time? So in continuous time, omega is going to infinity, but we know that actually this frequency is not reachable, is not possible in discrete time, because if we go over j omega s divided by 2, we end up in the secondary strip, okay? And the secondary strip is mapped in the primary strip and all the other strips. So everything that happens after j omega s divided by 2 is actually mapped inside the primary strip. So in discrete time, the maximum possible frequency is actually the frequency j omega s divided by 2. And we saw that this point over here, so the maximum possible frequency in discrete time, is mapped in the point -1. Okay, so we saw in one of the previous lecture that that point, so this point here in the S-plane, is mapped to this point here in the Z-plane. Okay, so in -1, because j omega s divided by 2 corresponds to basically e power j pi, okay, or e power minus j pi if we are over here, okay? So this is -1. So if we go back to the slide, so it means that the zeros at infinity, at s equal to infinity, are mapped into zeros at z equal to -1. What does it mean? It means that if our controller has a relative degree that is different from 0, then when we are mapping, we are using the pole zero correspondence, we have to add also a number of zeros in our controller corresponding to the zeros at infinity, so r zeros at z equal to -1. Finally, the last characteristic that we want to preserve is the gain. And the gain depends if we are considering the gain at s equal to 0, so for constant signals, or if we are basically considering the gain for s equal to infinity, so for high frequencies, okay? Where the gain at s equal to 0 is mapped? Well, the gain at s equal to 0 is mapped at z equal to 1, because the point s equal to 0 is mapped in discrete time in the point z equal to 1. And the gain at s equal to infinity is mapped in z equal to -1, because as we have just said, the point s equal to infinity in discrete time is mapped here, okay? When we want to use one gain and when we want to use the other, well, it depends. If the controller is a low-pass filter, so it means that has a certain gain for low-pass and then at high frequencies the gain is 0, then obviously the gain that we want to preserve is the one for s equal to 0. If instead our controller is of high-pass type, it means that for low frequency the value will be 0 and for high frequency there will be a certain gain, then the gain that we want to preserve is the one for high frequency, so the one for s equal to infinity. So this may be not clear up to this point, but let's make an example and this will clarify things very quickly. So we start with C of S, and we have that this is our controller, okay? And we want to compute, we want to discretize this using the pole zero correspondence. So first of all, we map S plus A in this pole here, okay? So this pole is mapped here using the first rule. Then we see that this controller has a relative degree of 1, so we want to add a 0 in the point z equal to -1, okay? Then A here is a constant that is mapped in here. And then finally, we want to compute the gain of this controller. To compute the gain, we have to compute the gain or for s equal to 0 or for s equal to infinity. For this controller, we want to compute the gain for s equal to 0. So to do so, we replace s equal to 0 in C of S, and we obtain A over A, okay? So we obtain 1. 1 is equal to C of Z, so this expression here, when Z is equal to 1. If we replace Z equal to 1, we obtain K, A, times 1 plus 1, so it's 2, divided 1 minus e power minus at. Okay? Now, this expression has to be equal to 1. We solve with respect to k, and we obtain this expression here. And we obtain our discrete time controller. With this discretization algorithm, we conclude the topic of indirect methods. And now we are ready to move on to the next method, so the direct methods of control.